So we're going to have a look at complex numbers and how to represent them on a plane. So just remember that a number can be written with a real part, say the number 2, and we're going to add another component, that's the imaginary component. So we just write it afterwards. Okay, so something like 2 plus 3i. So this form is called the Cartesian form. So how do you graph this on a number line? So typically you would have a straight line to represent the real value. Okay, so to do the imaginary part, we're going to use the y-axis. Now the symbol for real, we use an R that has an extra line. It's called a double struck letter. Okay, so for an imaginary one, we do an I with a double vertical line as well. You can also write RE in IM, meaning real and imaginary. So 2 plus 3i is just simply 2 across and then 3 up. Okay, and then we just put a dot there. Okay, so you don't draw a line, it's just that point that represents 2 plus 3i. If it was just 2, you place a dot on 2. If it was 3i, you put a dot exactly on 3i. Now you don't need to write the I on the vertical axis. Okay, so now you can also represent this complex number in a different way. It looks like a vector. So we can write it with a modulus. So I'm going to show you this first. We're going to join the origin to the complex number. Okay, so this part here is called the modulus. Now the complex number is named Z. Okay, so you previously have looked at numbers and we named those numbers as X. And you can have Y that is a two-dimensional number. Now they use the letter Z because it's a complex number. A complex number consists of real and imaginary. Okay, so this part here is called the modulus, and you write it like an absolute value sign. Okay. So in this example here, if you just do a little bit of Pythagoras to figure it out, this is 3 and this is 2. So 2 squared plus 3 squared, 9 plus 4, 13. Okay, so the modulus is root 13. Now we're going to also write something else. It's called the argument. Okay, so the argument is the angle, and it's marked here. Okay, just like with unit circle, you measure from the x-axis going anti-clockwise. Okay, called argument. Now I'm just going to quickly write the notation of showing you this other method. So you write the letters CIS. I'll explain to you what they mean later. CIS and then the argument. So in this one, we have to calculate what the angle is going to be. So again, we're going to use some trigonometry to figure out what the theta is going to be. So understand that you can use tan. Okay, so the theta in this example will be tan inverse of 3 over 2, and then it'll be equal to some angle. Okay, so we're going to go calculate what that angle is going to be. So we'll just use our calculator. Now with angle, eventually you'll have to write it in radians, but just for this example here, we can write it in degrees. So I'll just change it to degrees just so you can understand what it means. Okay, so second tan, 3 over 2. Alright, it's about 56.3 degrees. Okay. Alright, so we write 56.3 degrees. So this form is called polar form. Alright, so simply a complex number has a real part and an imaginary part. So we'll just mark those in again. Okay, so this is the real part. Okay, this is the imaginary part. And you can write it in a Cartesian form, as so. You can represent it on a plane. Now this special plane has a name. It's called the Argand plane. Okay, it's not called Cartesian plane. Also known as the complex plane. Okay. So you can also write this complex number in terms of a length, so the distance from the origin to the point, and also the angle. So the distance is called modulus, the angle is called argument, and you write it in this form. So now I'm going to explain to you what the cis means. Okay, so a bit more information about polar form. So if we look at a diagram of a general complex number, okay, so let's just put a point over here where we know this value here is called A and this is called B. So that means my complex number in Cartesian form is A plus BI. Okay, so Cartesian form. So to get it into polar form, what we want to know is this modulus, and we also want to know the argument. Alright. Now you need to understand there are some relationships here, okay? So the modulus, we can see equals the square root of a squared plus b squared. Okay, so that's actually the rule to calculate modulus. Now to get the argument, we can also write a little rule, and that's the tan inverse of b on a. Now be careful if the complex number is in a different quadrant, so maybe it's over here, you do need to use your understanding of the unit circle. Okay, so when you use tan inverse of b on a, it will always tell you the acute angle in the first quadrant. So just have a look at whether the b value is negative or the a value is negative, or if they're both negative, and it'll tell you which quadrant it's supposed to be, and then you'll write the correct angle. We'll have a look at that later when we see angles in different quadrants as well. So now you know there's a formula to calculate each of those values. Okay, more about what the cis means. So if you have a look at this component here, A, we can also write that in terms of the modulus and the argument. So you will see that A is the horizontal part, so simply A is the modulus of Z times the cos of the argument. Okay, so sometimes they like to label the modulus as the letter R. R meaning like the radius. Okay, this is the center of your circle, and you have a radius at this point and you draw a circle around it. That's why they use the letter R. Okay, alternatively you can also work out the vertical point. Okay, so this is the B value, so B equals the modulus of Z times the sine of the argument. Okay, so this is another set of useful conversions. Alright, so this one calculates modulus and argument. Mod arg. and this one calculates the real component and imaginary component. Okay, so these are the components. Okay. All right, so knowing this, okay, that means I can rewrite the real part in terms of the modulus and the argument, and this is how the polar form comes about. So this A here will be called modulus of Z cos theta, right? So that's my A, and then I'm going to plus BI. Okay, so B is modulus of Z, and then sine argument, and then I've just got an I at the end, so I'll just put this in brackets to show that's like a coefficient. Okay, so this is the B value. Now that's very long to write, okay? So what they did was they did a shorthand notation. They used the first letters of each of those trig functions. So you'll see there's a C here, S. Now the I typically is written in the front, okay? So it's an imaginary component. So it'll be a CIS, okay, instead of CSI, which would have been a coincidence with the TV show. So this is where that notation comes from. So the modulus is common in both. So if I factorize it out, I've got the modulus of Z, and then it's cos argument plus I times sine argument. So that's shorthanded as CIS. Okay, so this is called the polar form. Alright, so just to quickly recap, what have we looked at here? This is an introduction to how to represent complex numbers. You represent it on an Argand plane, and you can have two forms, Cartesian form, polar form. The polar form, you write it with a shorthand notation called the cis notation, and simply you just write the modulus in the front and then the argument at the back. So in the last couple of minutes of this video, just to do a couple of examples. So if you want to, I'll say plot, but it's really just draw Z equals -1 plus 3i, and then they usually name the other complex numbers as W, and then you've got 2 minus 5i. So what we're going to do, okay, draw our plane there. 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5, 1 2 3 4 5. So -1 plus 3i, -1 plus 3i is right there. And then typically we draw a line to the origin, label that one as Z. Okay, 2 minus 5i, 1 2, 1 2 3 4 5 down here. Okay, there's a point there, and we'll just label this one W. Okay, now they kind of look like they're in line with each other with the same gradient, but if you check it, it's not true. It's just my sketch makes it look like it is. Now, questions you could be asked are to convert these to polar form. So I'll draw another complex number. I'll just call it Z also. And you wanted to do 3 cis pi pi on 3. 3 cis pi on 3. Okay, so firstly what I would do is work out the argument. So pi on 3 means 60 degrees. And from here I need to draw a line that's 60 degrees. Okay, and then I just have a length of 3. 1, 2, 3. Okay, so that's my 3 cis pi on 3. And if you want to know what the exact values of the real and imaginary are, you just use this formula over here to figure it out. Alright, so lastly, note that there are formulas on the formula sheet, and we'll just have a quick look at how that appears. Okay, so we're doing topic 1. They give you the standard, the Cartesian form, and they also give you the polar form. There's the r cos theta plus r sine theta, and there's the r cis theta. We'll talk more about this version way later when we're doing proofs. Okay, and that's it.